In this video, we're going to talk about something called the left regular representation of a group. So just to give an idea of where this whole thing is going, I always feel like that's a good idea. If we're going to get into something complicated, let's give some motivation for it. So here's the idea of what we're going to do in this video. We're going to prove that every group is isomorphic to a permutation group. That every group is isomorphic to a permutation group. In other words, every group is really, in its soul and in its bones, a permutation group. That is a subgroup of some symmetric group, which is insane when you think about it. So we can prove that every group in the world is isomorphic to a subgroup of some symmetric group. I mean, what that means is that if we wanted to know everything about groups, everything there ever is to know about groups, all we have to do is understand all of the symmetric groups and their subgroups completely. Now, the bad news is that's pretty hard to do. Symmetric groups tend to be pretty opaque. But nonetheless, it's a remarkable result that every group is really a permutation group, and we're going to prove that right now. So just to give an idea of how this works, I've included here the Cayley table for D4, the dihedral group on a square. Cayley table for D4. And before we get into the proof of this, I'm going to just give an argument based on this example. So here's the idea. By left multiplication, each element of D4 acts like, or acts as, a permutation of the elements of D4. So, for example, if I pick an element, let's pick, I don't know, V is kind of entertaining, so let's pick V. So V acts on the elements of D4 like this. I'm just going to list out all 8 elements of D4 on the top row of this array. I'm going to use array notation for this. R0, R90, R180, R270. And then we've got, let's see, H, V, D, and D prime. Those are the 8 elements. And now, if I just think of multiplying on the left by V, and keep in mind, by the way, that when I read this table, like if I look at this, this entry here, this is saying that V times R90 is D prime. So this is the element that goes on the left, this is the element that goes on the right. Okay, so if I multiply everything on the left by V, so I'm looking at this row here, then let's see, V times R0 is V, V times R90 is D prime, V times R180 is H, V times R270 is D, V times H is R180, V times V, of course, is the identity, R0, V times D is R270, and I guess that leaves R90 for the remaining entry, V times D prime. All right, so this is a permutation of this set. R0, R90, R180, R270, H, V, D, and D prime. It's a permutation of that set, which means this is an element of what we would call S sub D4. In other words, the symmetric group on this set of elements here. Okay, so V is a permutation now, or V acts as a permutation on elements of D4. I could even, if I wanted, represent V, or V's permutation, in disjoint cycle notation. So I could take V and I could say V as a permutation is really the product of these cycles. So I've got R0 going to V, and then V going back to R0, so V flips those two. V takes R90 to D prime, and then D prime back to R90. V takes R180 to H, and then H back to R180, and finally V takes R270 to D, and then D back to R270. That would be V in disjoint cycle notation. So V is one element of S of D4. Now, if we think about the 8 permutations that we can get this way, because there's a permutation for each element of D4, that is each element's left multiplication, then am I going to get all of S sub D4? And the answer is pretty clearly not. S sub D4, this is a symmetric group on 8 elements. So its order would be 8 factorial, which is, I think that's 40,320 if I remember correctly. So we have 8 elements here that we're multiplying on the left by, so we're not going to get 40,000 permutations out of this, obviously. We're only going to get 8 special permutations, but those permutations, I claim, will be a subgroup of S sub D4. And that's part of what we're going to prove in this video. All right, so here's what we're going to do now. We're going to prove, let's see, let's pick a nice green color here. We're going to prove if G is a group, then the following function phi from G into S sub G, that's the symmetric group on G, or the set of all permutations, or the group of all permutations of elements of G. This function is a group homomorphism. And in fact, it is 1-to-1. Okay, but I need to tell you what phi is. So here's the definition of phi. That is the definition of the left regular representation of G. So the definition is, for each element G belonging to the group G, we define phi of G to be the permutation that maps X to Gx for every X in G. Okay, that is, that's left multiplication by G. Okay, now there's a lot to unravel here, and it can be a little bit confusing, because here I've defined a function. And I'm calling that function phi of G, but I might also call it something else, because we're used to calling permutations by the name, by Greek names like sigma. So I'm going to call this permutation sigma sub G. And sigma sub G is going to be the permutation that maps X to Gx for every X. So I think there's a few things to prove here. First of all, I need to prove that sigma sub G actually is a permutation. In other words, that it's a bijection. It's a bijection from G to itself. If I can prove that, then that means that sigma sub G is a permutation and therefore does belong to S sub G. And then once I've proven that, I need to prove all the usual stuff about phi. I need to prove phi is a homomorphism. And then I need to prove that phi is injective. All of these things need to be done. So I think I'm going to split this into a couple of videos. In this video, we'll go ahead and prove number 1, that this left multiplication by G really does permute elements of G. And then we'll prove the other two things in the other video. We'll prove that phi is a homomorphism and that it's injective. All right, so let's start with the proof of number 1. All right, so suppose sigma, or not sigma, suppose that G belongs to G, okay? And define sigma sub G from G to G by just the same way that we did earlier, by sigma sub G of X equals Gx for every X in G. That certainly defines a function, because I can always multiply any element of the group on the left by G, and that'll give me an element of the group. So I have no problem with this being a function. What I need to show is that it's 1-to-1 and not 2. So we need to show that sigma g is 1-to-1 and onto. Once I've proven this, I will know that sigma g is a permutation of elements of G. All right, so to prove that sigma g is 1-to-1, I'm just going to do the standard type of proof of one-to-oneness, which is, let's suppose x and x prime belong to G, and sigma sub g of x equals sigma g of x prime. And we will prove that x equals x prime. If I do that, then that means sigma g is 1-to-1. All right, well, if I've supposed that sigma g of x is equal to sigma g of x prime, that means that gx is equal to gx prime, because applying sigma g just means multiply everything on the left by g. And then by left cancellation, it's kind of rewarding how nice and easy this is now that we have cancellation laws. By left cancellation, x is equal to x prime. All right. So that means that sigma g is 1-to-1. Yay. All right, so what's next? Now let's prove that sigma g is on 2. And as always, the usual way to prove that something is on 2 is, let's let y belong to the codomain G. We will show there exists some x in G such that sigma g of x is equal to y. In other words, we will show that y gets hit by this function. Okay, now I'm just going to come over here in my thinking space and say, well, what would that look like exactly? Well, if I want sigma sub g of x to equal y, then that means I want g times x, because sigma g means multiply on the left by g. I want that to equal y. So the question is, what does x need to be? Well, I can solve this equation for x and get g inverse, just to knock off that g. Multiply both sides on the left by g inverse, and I get that x equals g inverse of y. So I think that's going to be a good choice of x. So that's what I'm going to pick x to be. So let's pick x to be g inverse of y, just what we said a minute ago. Then sigma g of x is equal to g inverse of y, because that's what x was, and that's equal to, well, that's just plain y. That's great, because that's what I wanted to show. I wanted to show that there's some x which maps to y. So sigma g is onto, because for any y in the group, I was able to find some element of the group which maps to y. All right, so sigma g is bijective, and therefore a permutation. Just for perspective, I want to go back real quick to what we were doing with D4. Let's just bring everything into the frame here, because I went to all this trouble to show that this sigma g is a permutation. And what does that mean in terms of real life objects? Well, you'll remember when we worked out the left multiplication by v permutation for D4, everything seemed to work out. Everything seemed to work out just so that every element of my group appeared exactly once down here in the bottom row. And remember, I generated that not just by guessing or reordering randomly the elements of D4. I did that by reading the multiplication table. So if I zoom in on the multiplication table, you'll notice we were doing left multiplication by v. So we were in this row of the Cayley table. And you'll notice that row contains every element of D4 exactly once. But that would be true no matter which row of the Cayley table you look like. I could do left multiplication by any element and see every element of the group appear exactly once. That's what it means for left multiplication to be a bijection. And that's not true of just D4, that's true of any group, and that's what we proved here. In the next video, we'll talk about why phi is an injective homomorphism.